The sixth knowledge area of PMBOK 5 is project time management, which includes the processes required to manage the timely completion of the project. Time management deals with the ability to plan and finish the project in a timely manner. The time management processes deal with defining activities, estimating the durations of activities, scheduling activities, and ensuring adherence to the schedule. Time management is a crucial part of any successful project. Without careful planning, projects are set up to fail. You'll notice that all of the processes, except for the last one in this knowledge area, belong to the planning process group. In the upcoming videos, I'll be covering each of these processes as well as the ITTOs involved. One thing that will be important to note for this module is that these processes must be done sequentially. You'll notice as we move along that the outputs of the first process will become the inputs of the second process, and the outputs from that process will become the inputs for the third process, and so on. So, keeping that flow in mind, let's move on to the 7 time management processes themselves. Plan schedule management, define activities, sequence activities, estimate activity resources, estimate activity durations, develop schedule, and control schedule. The second process, define activities, is the process of identifying and documenting the specific actions to be performed to produce the project deliverables. In this process, we are taking the deliverables that we identified at the lowest level in the WBS, referred to as work packages, from the Create WBS process in the Scope Management knowledge area, and are further breaking them down into tasks or activities. These activities represent the work effort required to complete the work package. This will then provide a basis for estimating, scheduling, executing, monitoring, and controlling the project work. The key inputs include schedule management plan. You'll notice that this was the output of the preceding process. A key input from the schedule management plan is the prescribed level of detail necessary to manage the work. And scope baseline. The project WBS, deliverables, constraints, and assumptions documented in the scope baseline are considered explicitly while defining activities. The key tools and techniques for the define activities process are decomposition and rolling wave planning, and these are integral to the outputs: activity list, activity attributes, and milestone list. The first method to define activities is decomposition. Decomposition is where we break down higher level components into lower levels, and this is done until it is acceptable to stakeholders for planning, delivery, and control. Essentially, each work package within the WBS is decomposed into the activities required to produce the work package deliverables. Let's look at a quick example here. So the work package, laying cables, has now been broken down into specific activities such as cut wall ducts, buy cables, put cables in wall ducts, and test cables. The technique we use to create the activity list here is called decomposition. Rolling wave planning is an iterative planning technique and a form of progressive elaboration, where the work to be accomplished in the near term is planned in detail and future work is planned at a higher level of the WBS. At the beginning of the project, near-term deliverables are decomposed into individual components or work packages and defined at the greatest level of detail. Deliverables and schedule activities that will take place several reporting periods in the future are more broadly defined. For example, phases 1 to 2 might be broken down fully in the WBS. Phases 3 through 6 might be outlined only to the level of sub-projects. Then, while schedule activities for phase 1 are underway, the detailed planning for phase 3 would commence. As phase 2 is put in motion, planning for phase 4 would start, and so forth. In this way, rolling wave planning permits work activities to move forward on current and near-term deliverables while planning is still ongoing for future work packages. Let's look at the key outputs of this process. Activity list. As we discussed earlier in this process, the WBS work packages are further broken down into activities or tasks. The result is an activity list, which includes all the activities that are required for the project in sufficient detail for others to understand what has to be done. The second output is activity attributes, which are the details associated with the activities. These are progressively elaborated throughout project planning. These attributes extend the description of each activity and can include activity identifier, WBS ID, activity label or name, and when completed may include but not limited to activity description, predecessor activities, and successor activities. The last key output is the milestone list, which is a significant point or event in a project. A milestone list is a list identifying all project milestones, and it indicates whether the milestone is a mandatory dependency, such as those required by contract, or optional, such as those based upon historical information. Milestones are similar to regular schedule activities with the same structure and attributes, but they have zero duration because milestones represent a moment in time. Watch for these outputs as they become the inputs for the next process. The third process is sequence activities, which is the process of identifying and documenting relationships among the project activities. The key benefit of this process is that it involves the mapping of task dependencies, so you can determine the logical sequence of work to obtain the greatest efficiency given all project constraints. To do this, the project manager will require the preceding documents. The ITTOs for the sequence activities process are as follows. Here, you can see that the key inputs in this process are actually the outputs from the preceding process. Schedule Management Plan. Again, it identifies the scheduling method and tool to be used for the project, which will guide how the activities may be sequenced in this process. Activity List. The activity list from the prior process contains all schedule activities required on the project, which are to be sequenced. We need to consider dependencies and other constraints for these activities since that can influence the sequencing of activities. Activity attributes may describe a necessary sequence of events or defined predecessor or successor relationships. And milestone list. The list may have scheduled dates for specific milestones, which may influence the way activities are sequenced. The key tools and techniques we use in this process are Precedence Diagramming Method, or PDM. Before creating a project schedule, you need to identify and understand the dependencies between project activities. Each activity is dependent on some other activity. When a dependency is not identified, the project will be delayed until such a time that identification occurs. Let's take a look at an example here. Precedence diagrams are also known as project schedule network diagrams that represents activities through the use of boxes, referred to as nodes, and connects them with arrows that show the dependencies. Basically, activities are graphically linked by one or more logical relationships to show the sequence in which the activities are to be performed. Activity on node is one method of representing a precedence diagram. This is the method used by most project management software packages. In PDM, finish to start is the most commonly used type of precedence relationship, but it can be used to show other types of relationships as you see in this figure. Let's give dependencies a more in-depth look. Types of dependencies. There are 4 types of dependencies that you need to be aware of before creating a precedence diagram. Finish to start. In this dependency, activity B cannot start until activity A has ended. For example, you cannot cook a stew before gathering all the ingredients. Therefore, the activity, gather ingredients, needs to finish before the activity, cook stew, can begin. This is the most commonly used dependency. Start to start. In this dependency, there is a defined relationship between the start of activities. So, both tasks A start at the same time. For example, leveling concrete cannot begin until pouring the foundation begins. Finish to finish. In this dependency, there is a defined relationship between the end dates of activities. So, both tasks finish at the same time. For example, writing a document is required to finish before editing the document can finish. Start to finish. In this dependency, there is a defined relationship between the start of one activity and the end date of a successor activity. This dependency is rarely used. It means that the completion of one task depends on the start of a later task. For example, the first security guard shift cannot finish until the second security guard shift starts. Another tool and technique is dependency determination. Dependencies can either be mandatory or discretionary, internal or external, or a combination of each. For instance, mandatory external. Mandatory dependencies are often referred to as hard logic and are inherent in the nature of the work, such as physical limitations, or they may be due to contractual obligations. If you are working on building a new product, a prototype has to be built before it can be tested. In a project, the project team will need to determine which dependencies are mandatory during the process of sequencing the activities. Discretionary dependencies, often referred to as preferred logic, preferential logic, or soft logic, are typically due to industry best practices or a desired sequence. For example, you decide that it is best to make door and window frames before the full structure of the wall is in place. External dependencies involve a relationship between project activities and non-project activities. These dependencies are usually outside the project team's control, unlike internal dependencies. For example, you need to ensure that the electrical company has connected the electrical supply before the cables can be tested. Internal dependencies involve a precedence relationship between project activities and are generally inside the project team's control. For example, you know that drywalling a wall should be complete before the painting can start. Note that this is also an example of a mandatory dependency. It's important that the project management team determines which dependencies are internal during the process of sequencing the activities. And third in our list of tools and techniques, we have leads and lags. A lead is the amount of time whereby a successor activity can be advanced with respect to a predecessor activity. A lag is the amount of time whereby a successor activity will be delayed with respect to a predecessor activity. Let's look at this example here. The key output is project schedule network diagrams, which are graphical representations of the logical relationships, also referred to as dependencies, among the project schedule activities. Here you can see what this looks like. As you can see here, the schedule network diagram visually depicts how all the tasks in your schedule string together. While the WBS shows you how many tasks you have to accomplish, the schedule network diagram shows the order those tasks need to happen. It's a great way for starting to understand and visualize how your project will proceed. In the context of project planning, a network diagram is a sequence of steps or activities commonly represented by boxes. They are linked together in the logical sequence they need to be carried out. Once the diagram has been completed, you have a clear picture of the required sequence of events and activities for your project. For example, you cannot start building your house foundation until you have first prepared and leveled the ground. It's important to include the project team in the development of the network diagram so you can get a consensus of understanding of how the project should be implemented. The fourth process is estimate activity resources. This is the process of estimating the type and quantities of material, human resources, equipment, or supplies required to perform each activity. The key benefit of this process is that it identifies the type, quantity, and characteristics of resources required to complete all activities, which allows for more accurate cost and duration estimates. The ITTOs for the Estimate Activity Resources process are as follows. Let's take a look at the key inputs for this process. The Schedule Management Plan, which identifies the level of accuracy and the units of measure for the resources to be estimated. The Activity List. It identifies the activities that will need resources. The Activity Attributes. They provide the primary data input for use in estimating those resources required for each activity in the activity list. Resource calendars. This comes from the Project Human Resource Management knowledge area and identifies the working days and shifts on which each specific resource is available. This includes the availability of human resources, equipment, and material during a planned activity period and is used for estimating resource utilization. The following are the key tools and techniques. Alternative analysis. Many schedule activities have alternative methods of accomplishment. They include using various levels of resource capability or skills, different size or type of machines, different tools, hand versus automated, and make, rent, or buy decisions regarding the resource. For example, you may have the option of either using an excavator or using shovels to move some dirt. Published estimating data. Several organizations routinely publish updated production rates and unit costs of resources for an extensive array of labor trades, material, and equipment for different countries and geographical locations within countries. For example, after reviewing public records, you determine that laying a brick takes approximately 10 minutes for an average mason. Also, we determine the resource quantities required for each activity or WBS component and roll it up to the entire project level. This method of estimating resources is referred to as bottom-up estimating. This can be performed using the WBS or activity list and when the scope is well defined. The outputs are activity resource requirements, which identify the types and quantities of resources required for each activity in a work package. These requirements can then be aggregated to determine the estimated resources for each work package and ultimately for the entire project level. The amount of detail and the level of specificity of the resource requirement descriptions can vary by application area. The resource requirements documentation for each activity can include the basis of estimates for each resource, as well as the assumptions that were made in determining which types of resources are applied, their availability, and what quantities are used. And resource breakdown structure. This is a hierarchical representation of resources by category and type. Examples of resource categories include labor, material, equipment, and supplies. Resource types may include the skill level, grade level, or other information as appropriate to the project. The resource breakdown structure is useful for organizing and reporting project schedule data with resource utilization information. And we'll see these two outputs become the inputs in the next process. Estimate activity duration is the fifth process, and it estimates the number of work periods, for example, the number of days or number of hours needed to complete individual activities with estimated resources. This process is important mainly because it provides the amount of time each activity will take to complete, which is a major input into the developed schedule process. The ITTOs for the estimate activity duration process are as follows. And notice that the key inputs are actually the outputs from the prior process. The key inputs are schedule management plan. This plan defines the method used and the level of accuracy along with other criteria required to estimate activity durations. Activity list. We need the activity list along with the associated activity attributes so we can determine duration estimates for each of them. Activity resource requirements. The estimated activity requirements will have an effect on the duration of the activity. For example, if our plan is to assign lower skilled staff to an activity on the project, we may need to extend the duration of that activity due to training requirements as well as the learning curve. Resource breakdown structure. Again, this is a hierarchical structure of the identified resources by resource category. The categories could include labor, materials, equipment, and supplies, and is a useful way to organize and report resource-related data. The tools and techniques are analogous or top-down estimating. This is when you use the actual duration of a previous similar activity or project as the basis for estimating the current duration of an activity or project. For example, you know from experience in working on prior projects that building each floor usually takes 6 months. So you use this estimate to help you come up with a duration estimate for this project. Analogous estimating is usually less costly and time-consuming than other techniques, but it is also usually less accurate. It is often used when there is little information about the project. Parametric estimating is an estimating technique in which an algorithm is used to calculate cost or duration based on historical data and project parameters. Parametric estimating uses a statistical relationship between historical data and other variables, for instance, square footage in construction, to calculate an estimate for activity parameters such as cost, budget, and duration. For example, you know that it takes 1 hour for the cable vendor to install 20 meters of cables. So you assign an estimate of 50 hours for installing 1,000 meters. When you think of parametric estimating, think of mathematical calculations. We also take use of the 3-point estimate. The accuracy of single-point activity duration estimates may be improved by considering estimation, uncertainty, and risk. This concept originated with the program evaluation and review technique, also called PERT. For example, in order to get a better understanding of how long it will take to create the foundation for the building, you decide to ask 3 experts for their estimates. This will provide you with a pessimistic, most likely, and optimistic value. With these 3 estimates, you will come up with an expected activity duration using a weighted average. Let's look at this formula. Reserve analysis. Duration estimates may include contingency reserves, sometimes referred to as time reserves or buffers, into the project schedule to account for schedule uncertainty. Contingency reserves are the estimated direction within the schedule baseline, which is allocated for identified risks that are accepted and for which contingent or mitigation responses are developed. Obviously, as more information about the project becomes available, the contingency reserve may be used, reduced, or eliminated. The key output is activity duration estimates, which are quantitative assessments of the likely number of time periods that are required to complete an activity. Duration estimates do not include any lags like what we defined in the sequence activity process. Activity duration estimates may include some indication of the range of possible results. For example, 2 weeks plus or minus 2 days, which indicates that the activity will take at least 8 days and not more than 12, assuming a 5-day work week, and 15% probability of exceeding 3 weeks, which indicates a high probability, 85%, that the activity will take 3 weeks or less. Develop schedule is the 6th process, and it analyzes activity sequences, durations, resource requirements, and schedule constraints to create the project schedule model. The key benefit of this process is that by entering schedule activities, durations, resources, resource availabilities, and logical relationships into the scheduling tool, it generates a schedule model with planned dates for completing project activities. The key inputs are the schedule management plan, activity list, activity attributes, project schedule network diagrams, activity resource requirements, resource calendars, and activity duration estimates. You will notice that all of these are from the prior processes in this knowledge area, and we already reviewed them. So let's take a look at some key tools and techniques here. Critical path method involves calculating the theoretical early start and early finish dates, and late start and late finish dates for all schedule activities. We do a forward pass to determine early dates, followed by a backward pass to determine late dates. Let's look at a quick example here. In this example, the longest path includes activities A, C, and D. Therefore, the sequence of A, C, D is the critical path. The critical path is a sequence of activities that represents the longest path through a project, which determines the shortest possible project duration. The critical path always has a 0 total float because any delay on that path will most likely result in a project finish delay. So we see then that there is no schedule flexibility. Also, any activity on the critical path is called a critical path activity. Critical chain method is a schedule method that allows the project team to place buffers on any project schedule path to account for the limited resources and project uncertainties that could affect the project schedule. For example, you realize that the building designs must be approved by a particular architect who may not be available as planned. Since this activity is on the critical path, you decide to modify the schedule by adding buffers at the end of your project to account for this in order to protect the target end date. Resource optimization techniques can be used to adjust the schedule model due to demand and supply of resources. Examples of resource optimization techniques include resource leveling and resource smoothing. Resource leveling is a technique in which the start and end dates of activities are adjusted so that supply and demand of resources is balanced. The supply of resources may be limited due to time or quantity, overallocation, or there may be a need to schedule them at a constant level. Leveling resources typically results in a longer critical path, so it's important to allocate scarce resources to critical path activities first in order to minimize the impact to the project schedule. Here is an example of resource leveling, and it shows a before and after scenario. You can see from this visual that Sue has been allocated to 2 activities during the same time period, so we can use resource leveling to keep resource usage at a more constant level and balance the demand for the resources with the available supply. In the second scenario below, Sue is now going to work on activity B on day 2, and Tom will work on activity C on day 3. Resource smoothing is a technique that adjusts the activities of a schedule so that resource requirements do not exceed resource limits. With resource smoothing, activities may only be delayed by as much as their float durations, so the critical path, and in turn the project's end date, is not affected. Modeling techniques. Let me cover 2 types of modeling techniques here. The first is a what-if scenario analysis, which is the process of evaluating scenarios in order to predict their effect, positively or negatively, on project objectives. We ask, what if the situation represented by scenario X happens? The outcome of the what-if scenario analysis can be used to assess the feasibility of the project schedule under adverse conditions and in preparing contingency and response plans to overcome or mitigate the impact of unexpected situations. Simulations involve calculating multiple project durations with different sets of activity assumptions using probability distributions constructed from the 3-point estimates to account for uncertainty. The most common technique is Monte Carlo analysis, in which a distribution of possible activity durations is defined for each activity and used to calculate a distribution of possible outcomes for the total project. Schedule compression is also a tool and technique here used to shorten the schedule duration without reducing the project scope in order to meet schedule constraints, impose dates, or other schedule objectives. There are 2 types of schedule compression techniques. Crashing means adding more resources. However, this may increase costs and risk. Fast tracking means doing things in parallel that would normally be done in sequence. However, this increases risk, such as rework. The key output of this process is the schedule baseline, which is the approved version of a schedule model that can be changed only through formal change control procedures and is used as a basis for comparison to actual results. It is accepted and approved by the appropriate stakeholders as the schedule baseline with baseline start dates and baseline finish dates. During monitoring and controlling, the approved baseline dates are compared to the actual start and finish dates to determine whether variances have occurred. The schedule baseline is a component of the project management plan. The 7th and final process of the project time management knowledge area is control schedule. It's the only one that doesn't fall under planning, but instead the monitoring and controlling process group. It is the process of monitoring the status of the project activities to update project progress and manage changes to the schedule baseline to achieve the plan. The key benefit of this process is that it provides the means to recognize deviation from the plan and take corrective and preventive actions, and thereby minimize risk. As the project activities are being performed on the project, the majority of effort in the project time management knowledge area will occur in the control schedule process to ensure completion of project work in a timely manner. The ITTOs for the control schedule process are as follows. The key inputs are project management plan, which contains the schedule management plan and the schedule baseline. The schedule management plan describes how the schedule will be managed and controlled. The schedule baseline is used as a reference to compare with actual results to determine if a change, corrective action, or preventive action is necessary. Another key input is work performance data, which is the raw information gathered about schedule performance and progress, such as which activities have started, what their progress is, and which activities have finished. Let me highlight a few key tools and techniques in this process. We have performance reviews, such as trend analysis, which examines project performance over time to determine whether performance is improving or deteriorating. Schedule performance measurements, such as schedule variance, or SV, and schedule performance index, or SPI, can also be used to assess the magnitude of variation to the original schedule baseline. Project management software can also be used for scheduling and provides the ability to track planned dates versus actual dates, to report variances to and progress made against the schedule baseline, and to forecast the effects of changes to the project schedule model. The key outputs are work performance information, the calculated SV and SPI time performance indicators for WBS components, in particular the work packages and control accounts, are documented and communicated to the stakeholders. Schedule forecasts are estimates or predictions of conditions and events in the project's future based on information and knowledge available at the time of the forecast. Forecasts are updated and reissued based on work performance information provided as the project is executed. Change requests can also be a likely output here. Schedule variance analysis along with review of project progress, results of performance measures, and modifications to the project scope or project schedule may result in change requests to the schedule baseline, scope baseline, and/or other components of the project management plan. Again, these change requests are processed for review and disposition through the Perform Integrated Change Control process. Any approved changes that result in changes to the project scope or impact activity resources or activity duration estimates would require the schedule baseline to be updated to reflect such changes. Before closing this module, let's take another quick look at the ITTOs for all of these processes so you can see how they really have to be done sequentially. The outputs from one process become the inputs for the very next process, whose outputs become the inputs for the next process, and so on. And that completes this important module on project time management.